Hi, can you all, oh, you can all hear me. Yes, all right, good. Good evening, welcome. Thanks for coming out on this beautiful spring evening. Um, Seriously, thank you for coming out on what is not a beautiful spring evening. I know it takes a little extra effort when ice is coming out of the sky. So my name is Gretchen Galbraith, and I serve as Vice President for Academic Affairs and Dean of the Faculty at St. Michael's. It's my pleasure to introduce Dr. Alain Brizard, Physics Professor and Chair of the Department at the College. An astrophysicist by training, Professor Brizard is one of the world's leading theorists in nuclear fusion and plasma. His research interests include thermonuclear fusion and space plasma physics. Professor Brizard earned his PhD in astrophysics from Princeton University and did his postdoctoral work in the Lawrence Berkeley National Laboratory at the University of California, Berkeley. Then we were fortunate to get him to come to St. Michael's. He arrived here in 2000 and was promoted to full professor in 2012. He is the author of over 100 peer-reviewed scientific journals, including some that have St. Michael's College students and alums as co-authors. His research is funded by the National Science Foundation and the U.S. Department of Energy. He's also a fellow of the American Physical Society and a member of the Vermont Academy of Science and Engineering. We are delighted to have Professor Brizard share his expertise with us today in advance of the once-in-a-lifetime, at least for most of us here, total solar eclipse on April 8th. He will help answer some of the simple questions. For example, why is this happening? And why are eclipses so rare? As well as the more complex questions, including which specific features people should be able to see in the sky on April 8th. He'll also discuss the history of the discovery of eclipses and how to be safe while viewing the upcoming solar eclipse next Monday. Please join me in welcoming Professor Brizard.
Well, welcome. If I was given the choice between weather like this today or Monday, I'm going to pick today. Yes. The title of my talk is A Solar Eclipse to Remember, Everything You Need to Know for April 8th. So this is a map, a version of a map that you all probably have seen already, showing the path of totality, starting in Mexico and extending all the way through a major portion of the US and leaving North America through Newfoundland. Maybe I need to. All right. So this is an animation that shows the center dot is the path of totality, and then you have various zones that describe the partial eclipse. Let's go back and run this again. You can see again various zones of partial solar eclipse, and the dot at the very center is the path of totality next Monday. So this is a rare event. And this slide essentially tells us why a total solar eclipse is so rare. So three conditions must be met in order to have a total solar eclipse. So the animation, the diagram here shows, and hopefully you can see my mouse. No. All right, and the laser pointer is not working. So I'm going to be moving around. So what you can see here, Earth moves around the Earth. Earth moves around the Sun on a plane called the ecliptic plane. And the word ecliptic is precisely, has that precise meaning. So Earth is moving on the ecliptic plane, And here, the moon is also orbiting the Earth on a different plane. And that plane, as you can see on your right, is tilted by about 5 degrees. So consequently, on the right here, we see 2 phases of the moon. When the moon is in front of Earth, then we cannot see it, and this is the phase of the moon called the new moon. When the moon is behind Earth, it's still impacted by the light from the sun, and from our perspective, this would be a full moon. As the moon orbits the Earth, it also crosses the ecliptic plane along a line that is known as the nodal line. So as we move counterclockwise at the top, we see the moon again orbiting the Earth, but this time, the moon can either cross the ecliptic plane in front of Earth, but in line with Earth and the sun, in which case the moon would partially or totally obscure the sun. That would be a total solar eclipse. Or it could be behind Earth, in which case the Earth would partially or totally obscure the moon. That would be a lunar eclipse. So the first condition, the moon must cross the ecliptic plane, but it does so every month. It crosses the ecliptic plane. The second condition, it needs to cross the ecliptic plane on a line that joins Earth and the sun. And the third condition is that the moon must be a new moon, not a full moon, because that would give you a lunar eclipse. A solar eclipse is when the moon is in its new moon phase. So these 3 conditions must be satisfied. So the moon has several periods. The first period of interest is called the synodic month, or associated with the period of lunation. And it's this typical well-known phases of the moon, starting from a new moon on the left, you can't see it, all the way to the full moon, and then back to the new moon. So once again, a total solar eclipse requires a new moon. And the synodic month is 29 days, 12 hours, and 44 minutes, and even seconds. So that's 1 month. Again, in order to get a total solar eclipse, you must have a new moon. Another moon is called the draconic month, and this is the month where the moon crosses the ecliptic plane, and it crosses the ecliptic plane, crossing the line between Earth and the sun. It's called the draconic month because the ancient Chinese believed that during a total solar eclipse, a dragon was eating the sun. And that's why it's called the draconic month. So this draconic month lasts 27 days, 5 hours, 5 minutes, and 35.8 seconds. A total solar eclipse, so March or April 8th at 3:26 p.m., we're going to have a solar eclipse. You may then ask the question, when is the next time we will have a solar eclipse, a total solar eclipse? So you need those 2 periods in time to match again in an integer fashion. So the Saros cycle was discovered by the ancient Babylonians and rediscovered by Sir Edmund Halley. So the Saros cycle is 242 draconic months. which is also equal to 223 synodic months. So that corresponds to 18 years, 11 days, and a third of a day. And I'll come back to a third of a day later. You might wonder, why were the ancient Babylonians so keen in determining or observing, finding out this Saros cycle? If you're a king in ancient Babylonia, again, the mythology of solar eclipses is that they were forbearer or of catastrophic events. If you're a king, you want to preserve your kingdom, and you want to know when is the next solar eclipse going to occur. And so the king had an armada of observers, observing the night sky, observing the fine details of when total solar eclipse occur, and when and where they occur. So I find it absolutely amazing that the Saros cycle was discovered more than 4,000 years ago. But that information was lost and rediscovered by Sir Edmund Halley of Halley's Comet fame. And so Halley was a close friend to Isaac Newton, I should say Sir Isaac Newton as well. And so Halley, rediscovering the Saros cycle, was able to predict a total solar eclipse in London to within 4 minutes of the actual event. So forecasting the occurrence of solar eclipses has been possible for many, many hundreds of years. I'll come back to the Saros cycle later on. So about a week ago, or 14 days ago, on March 25th, there was a lunar eclipse. And the lunar eclipse means that the moon was on the outside of Earth in line with the sun. 14 or half of a synodic month later, we're back in front of Earth, and now we have a total solar eclipse. So lunar and solar eclipses are always connected by either plus 14 days or minus 14 days, depending on whether the moon is crossing the ecliptic plane on the way up or on the way down. So here's an animation of the solar eclipse, the lunar eclipse that took place. You can see here that we're now moving out of the lunar eclipse. And that lunar eclipse was visible in North America. So this slide shows the shadow of the moon on August 11th, 1999, from the Mir space station. So this was a Russian space station. And you can clearly see here the shadow of the moon on Earth. And on the right, we see the lunar eclipse that took place on November 8th, 2022. So this is a little bit what, especially the left slide, the left photo, very few people have the opportunity to see this in person. So here's, again, to summarize a total solar eclipse: the sun on the left, the moon between Earth and the sun, and the moon is casting a shadow on Earth. So the smallest shadow will be where the total eclipse is seen, and that is called the umbra, the shadow of the moon. And then there will be a larger portion of the shadow or the solar eclipse itself, and that's the partial solar eclipse. And that partial solar eclipse is in a region called penumbra. So in 2017, we were in the path of a partial solar eclipse. And many of us on campus saw that partial solar eclipse. But on Monday, we'll be in the path of totality, as it's called. So this is, of course, very exciting. So there's a little bit of geometry involved with the solar eclipse. It turns out that the fact that the moon can eclipse the sun is just a matter of mathematics. In other worlds, it's certainly possible that the moon of a planet could not even completely block the surface of its home star. It just so happens on the right that the moon is at the right distance from Earth, and the sun is at the right distance of Earth, that they have the same what is called angular diameter. And this is how a total solar eclipse occurs. The moon's diameter is about 400 times less than the diameter of the sun, and the distance between Earth and the moon is about 400 times less than the distance from Earth to the sun. So this is just a matter of coincidences. So if we look at the angular diameter of the moon at apogee, namely when it's the farthest away from Earth, its angular diameter is measured in degrees and is 0.491 degrees. At perigee, when it's the closest to Earth, its angular diameter is 548. So Sunday night, the moon's angular diameter will be at 0.548. But it's a new moon, we won't be able to see it. If it were a full moon, it would be called the supermoon. At apogee, when a full moon occurs at apogee, it's visibly smaller, and it's often called a micromoon. The Earth also orbits the sun along an elliptical orbit, so it turns out to be closest to the sun in January. And that phase of the orbit of Earth around the sun is called perihelion. And at perihelion, the angular diameter of the sun is 0.542. When Earth is at the farthest from the sun in early July, called aphelion, its angular diameter is 0.524. So we have the largest new moon with an angular diameter of 0.548 degrees. And right now we're sort of in the middle between January and July. So the angular diameter of the sun can be taken to be 0.533 degrees. That means that there's going to be a period of time when the moon will completely cover the sun for a little while. Right? If they were exactly the same diameter, totality would last 0 seconds. The fact that the moon is larger than the sun on Monday means that the period of totality for us will last 4 minutes and 28 seconds. In July of 2186, I won't be around. The moon will be at perigee, and the sun or the Earth will be at aphelion. So the sun will be the smallest it can be in our sky, and the moon will be largest in our sky. That totality will last about 7.5 minutes. So that's what this geometry of a solar eclipse means. The fact that we're at perigee, that's how you can calculate the duration of totality. It's just a question of mathematics. Easy for me to say. All right, so that's the path, well-known path of the zone of totality for the eclipse on Monday. An interesting aspect at the bottom here is that it enters Texas traveling at 1,600 miles per hour. You have to think that the moon is moving, the earth is rotating, everything is moving. And you're just following a dot, essentially what appears to be a dot. The zone of totality is about 100 miles across. So that dot is moving quite rapidly. So it enters Texas at 1,600 miles per hour and leaves Maine in excess of 3,000 miles per hour. So it's moving. Let's come back to the Saros cycle. What is absolutely amazing here is that each solar eclipse belongs to a family called the Saros series. Each Saros series contains about 70 to 71 solar eclipses. They begin as partial solar eclipses, then transition to a hybrid or annular form of a solar eclipse, and then about 30 in the middle correspond to total solar eclipses. And then they end hybrid, annular, and then back to partial solar eclipse. So Saros 136 is shown here. We have 9 solar eclipses of Saros 136 from 1901 to 2045. I want to draw your attention on the right-hand side, the lowest blue band. That's the zone of totality for May 18, 1901. The next member of the family will be 18 years later, 11 days later, and 1/3 of a day. So 18 years, 1201 plus 18 is 1919, check. 11 days later, we go from May 18th to May 29, check. 1/3 of a day means that you go 1/3 around the Earth. That's 1/3 of 360 degrees, so that means that the eclipse will have moved 120 degrees ahead. And you can see May 29, 1919, and then the next member in 37, and then you're supposed to move to the right, and you show up on, this way. So June 20th, 1955, and then so on. So it's very easy to predict solar eclipses if you know about the Saros cycle and the fact that each solar eclipse belongs to a series of solar eclipses. So Saros, with an even number, they all begin at the South Pole. And they progressively migrate northward until they disappear at the North Pole. That's for an even number of a Saros series. If you're, again, good in math, 3 times 1/3 is 1. So if you have 3 Saros cycle, you will get 54 years and 34 days. So you can see here that the stack of solar eclipses are all separated by 54 years and 34 days, and they migrate northward. For Saros 139, which is the solar eclipse we will see on Monday, started at the North Pole and is progressively migrating downward and will disappear at the South Pole. On the right-hand side is the zone of totality for the solar eclipse on April 8th. And the animation on the left is showing all the solar eclipses that belong to the Saros 139 family. So we see here it's progressively moving southward and then disappear. So the Saros 139 started on May 17th, 1501. And that's the crazy part of all this. We could probably give the time of day when the eclipse started on May 17th, 1501. I mention Michelangelo's David here because Michelangelo got the contract for making the statue David in 1501. Was completed in 1504. So that's how long ago. The eclipse we will see on Monday belongs to a family that started in 1501. And it will end on July 3rd, 2763. We could probably also predict when the solar eclipse is going to take place. But we know that the 1501 solar eclipse was a partial solar eclipse. We know that the 2763 eclipse will be a partial solar eclipse also. There are currently about 40 Saros series actively taking place during this era, if you will. So I think this is pretty cool. You know, when I was thinking about creating a presentation for the solar eclipse that you're here tonight, I thought, all right, so the moon is going to come between the sun and the earth, so okay. But then you started digging and then finding the Saros cycle, and this is absolutely amazing. It's rare and it's amazing. So this slide shows the next 10 solar eclipses, solar eclipses in the next 10 years. So the darkest red, of course, is April 8th. It's still in the future. And then other solar eclipses, and you can see here, over the next 10 years, the US will not be able to witness a total solar eclipse. That does not include partial eclipses and annular eclipses and so on. I'm just looking at total solar eclipses. This is even crazier. So you can do calculations and you can generate a map that you're seeing right now. So this map contains all the total solar eclipses starting from 2000 BCE to 3000 CE. All right, so 5,000 year record. The dark blue here shows a location on Earth when during that 5,000 year period, less than 5 solar eclipses have been observed. And the portions that are in yellow, these parts of Earth have witnessed total solar eclipses greater than 30 times in that 5,000 year period. The eye naturally very quickly observes that the northern hemisphere tends to see more total solar eclipses than the southern hemisphere. And there are some technical reasons for this, but this is an amazing map. Essentially, everywhere on Earth, if you wait long enough, you will be on the path of totality of a solar eclipse. An annular eclipse, I've already mentioned annular eclipse. An annular eclipse is when the moon is at apogee. It's smaller in size. It's not able to completely cover the surface of the sun. So what happens then is that it leaves a ring of the sun that is still visible. That's why it's called an annular solar eclipse. So on the left here, I show the difference between a supermoon, namely a full moon at perigee on the left, and on the right, we have a full moon at apogee, where it's smallest in the sky. It's definitely noticeable. Safety, safety, safety. So on Monday, we will be looking willingly, we will be looking at the sun. So obviously, you should not do that without special glasses. So these special glasses are called solar eclipse glasses. And for the students, staff, and faculty on campus, we have about 1,800 solar eclipse glasses available for students, faculty, and staff. We'll have more than enough solar eclipse glasses. So these are not sunglasses. So the glass itself is 100,000 times darker than sunglasses. They're made of a polymer that is a resin that is infused with carbon particles. If you wear solar eclipse glasses right now, you would see nothing. And that's the purpose of the solar eclipse glasses, so that when you look at the sun, you're able to see a greatly reduced amount of visible light, enough that it is comfortable to look at. And because it absorbs all of the ultraviolet radiation coming from the sun, your eye is not in jeopardy of suffering or experiencing damage to the retina of your eye. So that's an important aspect. And just to verify whether solar eclipse glasses, you may have already purchased solar eclipse glasses. They must all exhibit the ISO certification 12312-2, and in order to be certified as valid. If you don't see that number, that ISO number, do not use those glasses. So it's an important, so the bottom frame is showing the backside of the solar eclipse glasses with the ISO logo and a lot of information. That information certifies that these glasses are appropriate to watch the partial phase of the solar eclipse. So this slide here shows the progression, let's say from the left, when the moon is first contacting the surface of the sun. So the partial eclipse phase, people will have to wear solar eclipse glasses. When the surface of the sun is completely covered by the moon, the so-called totality period, then it will be safe to remove your solar eclipse glasses. On campus, we have purchased an air horn, and at the beginning of totality, I will sound the air horn. There will be no doubt that this is an air horn blaring. And then for about 3 minutes, we'll be able to see the hidden side of the sun, namely the solar corona. So it'll be safe to remove glasses, take pictures until you're blue in the face, but really, it's 3 minutes in your lifetime. Put the phone away. Put the phone away. Observe the corona with your eyes, with your friends, with your family, instead of, oh, I saw the eclipse. No, you looked at your phone. And then when totality ends, I'm going to again sound the air horn, indicating that you must now put your solar eclipse glasses back on, and then we have essentially the reverse of the first phase. So it starts at 2:14 and ends at about 4:30. But totality lasts a little bit more than 3 minutes for us. I mentioned earlier 4 minutes and 28 seconds. That's if you were at the center of the zone of totality. We're a little bit off. So for us, it'll be about 3 minutes and 19 seconds or something like that. All right? So we're a little bit off, and but it's still exciting. All right. So the next few slides, keep in mind that this presentation will be on the Total Solar Eclipse webpage on the St. Michael's website. So I'm not going to go through every single frame-by-frame description of what is going to happen. So you'll be able to look at this and see sort of the play-by-play. But the left frame summarizes the total solar eclipse on Monday. Starts at 14:14:14. Totality begins at 15:26:07. The maximum is at 15:27:45, and totality ends at 15:29:23 seconds, and then a partial eclipse ends at 4:37 and 20 seconds. Voila, we're done. I'll see you on Monday. No, all right. So let's look at a little bit more detail here. So on the right, we're beginning the solar eclipse itself. This is called first contact, and then we move on, and then the partial solar eclipse is deepening, and at 15:25:47, the solar corona starts to appear. So we're at the bottom right. Before then, so we see here at 14:57, the brightness of the sky, as the surface of the sun is progressively covered by the moon, the light will get fainter and fainter. So you're going to start noticing that something is happening. The temperature, the humidity, the wind will change, the level of light colors, and so on. Birds, there are birds that are diurnal and nocturnal. The nocturnal birds, of course, are waiting for the sun to set. Suddenly, as we near totality, the skies are getting darker, so the nocturnal birds will start to sing. And they don't know that there's a solar eclipse going on. So there's a lot of natural events that will be noticed. And then at 15:25:57, as the surface of the sun is almost entirely covered by the moon, in a desperate attempt, the sun is making us know that it's still there. So we see a very faint sliver of the sun, generating an effect that is called the diamond ring. And I'll show you a photo in the next slide. So that's what we are excited about seeing. And then, as you hopefully know, the moon is not a perfect sphere. It has craters, it has mountains, valleys, and so on. So as the moon is again creeping in front of the sun, sunlight will be able to come through the valleys at the surface of the sun and will produce an effect called the Bailey's beads. So that's at the bottom on the left side. And then shortly after that, totality begins. And we'll be able to see the mysterious glory of the corona. That sounds good, doesn't it? I like that. All right, the mysterious glory of the corona. And continuing until, well, here's the diamond ring on the left. I don't think, I've never seen diamond rings like this, but you get the idea. So what we see here, the bright spot on the right-hand side is the sun still looking at us, and the rest of the image is showing the corona of the sun. And on the right, you see at the bottom left at about 7 o'clock are the Bailey's beads. You see little bits of bright light separated by dark bands. The mystery, I should have changed the title. So the mystery of the corona. So as a plasma physicist, as an astrophysicist, of course, the sun is, as my son would say, is a giant ball of plasma, hot gases, and so it has been a topic of research, intense research, for many, many, many years. One mystery among many left of the sun is the solar corona, which can be observed only during the totality phase of a total solar eclipse. So we see here on the left the solar corona. We can see the solar corona because the visible part of the sun is completely blocked by the moon. Without that, the sunlight, the visible part of the sun, is so bright that it's nearly impossible to see the corona during the day. Only at totality are we able to see the corona. So you see here what appears to be fingers extended into space. This is where the solar wind comes from. So the sun is losing mass and is spewing matter and magnetic fields into space. And on the right is basically saying some of the features that are of interest. One of the most important aspects of the solar corona is that it is very hot. It is about 1,000,000 degrees, while the surface of the sun is about 6,000 degrees. So we still don't know why the sun's corona is so hot. So anytime you have the opportunity to observe one of the remaining mysteries of solar physics, namely the solar corona, it's an amazing opportunity. And then we go through the maximum of a solar eclipse, and then we do everything in reverse. Bailey's beads first, and then the diamond ring, and then the partial solar eclipse phase until the last contact. So the total eclipse will bid us farewell at 1637 on Monday. And then you try to go home from wherever you are. So I mentioned to you that that's not the only special part about the solar eclipse on Monday. The sun undergoes a cyclic period of minimum activity and maximum activity. connected to the number of sunspots visible at the surface of the sun. So this is showing you the sunspot record since looks like 1995. And you see that the bottom row shows the historical record of the sunspot number all the way back to 1750. And it's a fairly regular cycle of about 11 years. It varies, sometimes 9 years, sometimes 12 years, but it's fairly regular. So we started numbering 1 all the way to 23, reaching a peak activity, a maximum activity in July of 2000, and this is where my family and I crossed the bridge from New York to Vermont on the Bastille Day of 2000. And Bastille Day of 2000 also corresponds to one of the largest recorded event where the sun spewed out a large amount of matter in magnetic fields called coronal mass ejection. So what we see here, cycle 24 was a little bit reduced, and cycle 25, the gray and red band shows the prediction of the number of sunspots visible at the surface of the sun. And we can see here the zigzaggy blue line is actual data. So we are entering the maximum period of solar activity a little bit sooner than predicted. And consequently, there is a chance that when we look at the solar corona on Monday, we could see something quite spectacular. So how would this look like? So this is not an animation on the left. This is a coronal mass ejection. And I don't even need to know to tell you which part of what you're seeing is the coronal mass ejection. The white circle is the visible part of the sun. And you see that it has been blocked almost twice the radius by a mask to prevent you from seeing the solar corona and the visible part of the sun. But what you can see here is a large expulsion of matter and magnetic fields from the sun. And that would be quite exciting. On the right, you see the Sun-Earth connection. The sun produces a solar wind and periodically, not periodically, but sometimes launches out into space a coronal mass ejection. Fortunately for us, Earth is shielded by a magnetic field. And that magnetic field basically reroutes the solar wind to the geomagnetic north and south pole. And that wind then interacts with the atmosphere of the Earth and produces auroras, both at the north, aurora borealis, and the south, aurora australis. But if a coronal mass ejection has the right magnetic field polarity, it is possible to penetrate the magnetic shield of the Earth and do serious damage to orbiting satellites. So this is a very, very important part of our modern world. We rely on satellites for many aspects of our daily lives. But these satellites are potentially jeopardized by coronal mass ejections if they're able to penetrate the magnetic shield of the Earth. So we never know whether a coronal mass ejection is going to be able to do damage. The International Space Station has a special room dedicated to allow the astronauts to be protected from the radiation that is produced during what is called a magnetic storm. So solar eclipses have occurred for centuries. According to a human historical record, of course, they've been going on for billions of years. One of the more famous recent solar eclipses took place on May 19, 1919, and two expeditions were sent to Brazil and an island called Principe off the coast of Africa to witness the total solar eclipse of 1919. 3 years earlier, Albert Einstein had developed this theory of general relativity that predicted that the starlight in the vicinity of the sun should be curved by the gravitational field of the sun. Of course, when you look at the sun during the daytime, it's so bright that you can't see stars in the vicinity. But during a total solar eclipse, the face of the sun is completely covered, and then you're able to see stars in the vicinity of the sun. So on the left, the expedition was able to detect positions of stars and their shift according to where they should be without the presence of the sun. And on the right is an analysis of this deflection showing the results of Albert Einstein's theory. So the lines here match very well with the experimental data points. And at the lower right, you see the Newtonian result. So Newtonian gravity cannot explain any of these observations. Overnight, Albert Einstein became a world-famous physicist. Before that solar eclipse, the name of Albert Einstein was known only among a circle of physicists around the world. But because of that solar eclipse, you all know the name of Albert Einstein. There are other eclipses, minor eclipses of the sun. One of them is actually very rare, and it's called the transit of Venus. As Venus orbits the sun, once in a while, it is seen from Earth marching across the surface of the sun. That's called the transit of Venus. It's very rare. I'm going to go to the third bullet here. Only 4 pairs of transits have been observed since 1630. And the last pair that was observed in 2004 and 2012, each pair is separated by 8 years. I was lucky enough to observe the 2012 transit of Venus. I have bad news. The next one will be in 2117. I don't know about you, I won't be here. All right? So very, very rare event. Mercury, because the planet Mercury is closer to the sun, orbits at a higher speed, so the transit of Mercury occur more often. They're still rare, but they occur more often. All right, we're almost done here. On Monday at UVM, an astrophysicist will give a talk about stellar eclipses, and in particular how a stellar eclipse allows you to identify, to discover extrasolar planets. So on the right here, you see a star. and there's a planet that orbits that star, and it progressively moves in front of that star. And the lower right, you see the brightness of the star shows a little dip. As long as the planet is in front of that star, its brightness is a little bit lower. And then when the planet moves away from the surface of that star, the brightness goes back up. So that's how we discover extrasolar planets. That's one method. And it's a very common method of detecting extrasolar planets. Turns out that it works really for large planets, what are called Jupiter-like planets. But it's still exciting that with methods like this, we've discovered in excess of 2,000 extrasolar planets. And one of the major tasks of the James Webb Telescope is to observe, to detect extrasolar planets, and to analyze their atmospheres, to see whether life is possible on these extrasolar planets. I like this one. This is good. So this is a diagram showing the daytime sky on Monday around 3:30 p.m. And I call that a planetary family portrait. All the known ancient planets will now be visible in the sky in the vicinity of the sun. Of course, the moon, don't ask me where the moon is. All right? It's going to cover the sun. Mercury is going to be upper left. Venus will be to the right. Jupiter on the left. And then Mars and Saturn will be almost on top of each other. And this is an exciting time. We will be able to see all major planets in the solar system, well, major ancient known planets in the solar system at the same time as the moon, and hopefully we'll see the solar corona, the sun peeking out. I'm still here. So that's quite exciting. And what you all wanted to know, what we've been monitoring for a few weeks, what will the weather be on Monday? I know, yeah, fist pumping. This is great. I was going to show a map of the average cloud cover this region on April 8th, and it was not good. It was not good. But I think my wife and I were looking at weather conditions in Texas and Arkansas and so on. We're going to be in a very, very good position. We're going to be in a very, very good position. So that's it for my talk. I want you to experience a once-in-a-lifetime event. Your grandchildren will ask you one day, Grammy, Grandpa, where were you on April 8th? Don't tell them you were looking at your phone. All right? Experience this event. And experience the, what did I say, magical mystery of the solar corona? Yeah, that's got to be worth, and I don't know how busy your life is, but come on, 3 minutes. Get out and observe the this totality of that and the spectacle that the sun will give us on Monday. If you're a surgeon in the middle of surgery, stay there. But otherwise, get out of your office, get out of your house, and enjoy this experience with your neighbors. Thank you.
We have some time for questions from Professor Brizard, if anybody has any questions, but there's a few from the Zoom first that I'd like to pose to you. The first is, how dark will it get during totality?
So will be corresponding to the light level associated with full moon. So it will be dark, but you certainly can see each other, and it's not complete darkness.
And the second question is, can Dr. Brizard please repeat the number for certification on the solar eclipse glasses?
So it's easy, 12312-2.
And if there's any audience questions, I ask that you please hold until I reach you with the microphone so it can be heard through the live stream.
All right, we have a question in the front.
Question for you. When you talk about the solar corona that we'll be able to see, is that something that is just always there?
Always
that
there.
we just can't see, but now we get the chance to?
Yep.
Okay, and then also, does the solar eclipse, does the moon being in this position actually do anything to the sun? Change its composition, do anything to it?
No.
No, the sun it's not affected, but our visual interpretation of the sun is what changes.
Yeah.
Okay, thank you.
You've seen perhaps movies of painters trying to represent a three-dimensional feature in their painting. And a painter would often stretch her thumb outward, right? And right now my thumb does not cover your face. So I'm able to paint you in the foreground with the right perspective. People in the back, my thumb easily covers your face. So I can draw the people in the back again with that perspective. So that's how you've seen those painters, you know. So it's the same idea. Incidentally, the moon is moving away from Earth as a result of tidal forces and so on and so forth, I think a few centimeters per century. So if you come back 1 million years later from now, the moon will be farther away and maybe will no longer be able to cover the entire surface of the sun, and consequently 1 million years from now, I'm spitballing here, we could only have annular solar eclipses.
I had a question. As someone who studies the sun the way you do, is there anything you hope to see during this?
Professional solar physicists are not waiting for a solar eclipse to occur to study the sun. We have an armada of satellites constantly observing the sun. We pay close attention to sunspots because this is the expected location where coronal mass ejections are produced. So unfortunately, professional physicists, like professional astronomers, astronomers no longer put their eye to an eyepiece and moving a large telescope. Everything is at a computer desk, and you press buttons, and you have detectors and so on that measure this. So professional solar physicists have already started to study the sun. They've been studying the sun for a very, very long time. The important aspect of the solar eclipse on Monday is you. The general public is now able to experience the magnificent mystery of the solar corona, so that you get excited. And then the next time we need to fund important science projects, that at least you have a sense of what we experience on a daily basis. You know, physicists, I speak as one, are tremendously lucky to be paid for what we do. because we don't work. I've never worked a day in my life. I enjoy what I do. I'm 67 years old and I can't wait, my wife will attest, I can't wait to go to work in the morning. I enjoy what I do. And now the general public will get some of that excitement. And then that's the key part, why all of us witnessing this solar eclipse is so important. Not for the physicist, but for the general public, for the young girls and boys, right, who will experience something that perhaps they will experience again in the next century. We won't.
You mentioned the sun-eating dragon of Chinese folklore. Are there other interpretations from over the centuries that have captured you?
Yeah, I read something interesting. So the kings in Babylon would have the forecast of a solar eclipse in the future. So the king would actually abdicate and appoint another king, a fake king, and wait to see what's going to happen. All right? Because I don't want to die because I'm the king, but if I have a fake king, well, maybe I'll survive this. If nothing happens after the next solar eclipse, all right, you're out of a job, I'm back. So I think it's interesting. Another interesting story, Christopher Columbus was on the island of Jamaica in 1501, I think. And he knew that a lunar eclipse was going to happen on March 1st. So his ships were running out of food, running out of supply, and as the saying goes, the natives were getting restless, and Columbus was not able to broker a deal to obtain supplies and food, and he knew that the next morning there was going to be a lunar eclipse. So Columbus basically told the chief of the tribe, if you don't give me supply and food, something will happen tomorrow at moonrise. And sure enough, the next day, the moon rose and progressively became redder and redder and redder, to the great terror, of course, of the native population. They implored Columbus to stop this, and Columbus knew exactly how long the lunar eclipse would last, so he acquiesced to their demands only when he knew that the lunar eclipse was going to end. The lunar eclipse ended, everybody was very happy and impressed, and he got food and supply. So throughout history, of course, there are a lot of anecdotes like this where knowledge of solar or lunar eclipses could be used to their advantage.
So you mentioned that there was like, I forget the exact name, but there's like groups or the families of different solar eclipses. The one this solar eclipse being in was started about 1500s, ending about 2700s. And you said there's about 40 of them. So
there are 40 active Saros series. 139, 136, and so on.
So does that mean that every like 30 to 40 years you get a new one? Or are they not very
It's you get new families that are created. If the moon is descending as it's crossing the ecliptic plane, then that eclipse will start at the South Pole. Saros 139, all the eclipses are started at the North Pole, and so consequently, it's possible to predict when new Saros families will start.
Yeah, and then also, I wonder if you could use a welding helmet as a replacement for the glasses? Because I'd imagine
So
blocking
it
out
is possible. The welding glasses have ratings. I think they're called gauge. And so the question you have is that there's no ISO number. You don't necessarily know what the gauge of that welding glass is. Or you pay $3 and you know that your eyesight is going to be preserved. Your call. So it's, you know, in the old days, of course, we would take negative films and stack them, but we don't do that anymore. We have a much safer way of observing the partial phase of a solar eclipse.
Can you tell me if there have been studies done on the nature of retinal damage for those who are not protected, and if this extends outside of humans to animals who just happen to be in the vicinity?
I would say, it's just a guess, animals are brighter than us. They know not to look at the sun. So they're going to be okay. Studies, yes. There are different levels of damage to the retina. I'm not... My wife likes to say I'm the wrong kind of doctor, so I can't tell you specifically what, but don't plan on those.
So on a normal sunny day, you can go out and look at the sun.
With solar eclipse glasses.
Even without, on a normal sunny day, you can just wear sunglasses, or sometimes you can just look at the sun, no damage, that I know of. What's different about an eclipse that you have to be protected?
Well, my short answer is that you shouldn't. You shouldn't look at the sun for an extended period of time. And how long that period of time is, I don't know. So you're playing Russian roulette. Is that my short answer? It may be a little bit not what you wanted to hear, but don't.
I was noticing that the totality when it leaves in the northeast of North America is about 2 minutes. How much totality are they getting at the start when it starts down in Mexico? And then another question I have is what is the average amount of totality people do see?
Well, so I think Mexico will see a fairly longer, it's moving slower. So totality will last a little bit longer, in excess of 4 minutes. For us, at our location, I think the center of totality is almost hitting St. Albans. And they're maybe 3 minutes and 40 seconds, but it's moving faster. So it's just, in terms of an average is about 3 minutes. But again, I implore you, just leave the phone aside and just look. You'll be able to take off your solar eclipse glasses, and by all means, look at the sun then. And see what you can see. And this is something that you most likely will not see again in your lifetime. Let's see.
Is there a way to videotape or record the solar eclipse for?
So provided your camera has a special lens, then yes, you can videotape the event. I have a telescope that is equipped with a solar lens, and I'll set up the telescope as I did in 2017, and we'll be able to observe the sun a little bit closer. But a little bit closer, a telescope is overkill. Large binoculars would be fine, again, with the proper solar solar lenses. Large binoculars would be fine. A telescope, it's overkill. You're looking way too close. And unless you want to have the all-time best photo of a diamond ring or the Bailey's beads, which are hard to predict where they're going to be. There are, of course, professional solar eclipse chasers, and they have camera equipment, and they have a little bit more experience. But again, it's 3 minutes. Just observe what you see.
Hi, first I would like to say thank you so much for doing this.
You're welcome.
This is, I didn't know any of this. And my question is, if we are lucky enough to see the sun expel gases or whatever you call that, would that hurt our eyes if we're looking at during totality?
No. A coronal mass ejection takes on average 48 hours to reach Earth.
So we'd see it?
We'd see it.
But it
light
wouldn't
travels
hurt us
very
yet.
fast. Yeah.
Oh, good.
Yeah.
And we have to wait till all those beads are gone
Yeah.
before we can take our glasses off, right?
Yeah. On campus here, I'll blow the air horn. I don't know where you live. Maybe you'll hear it. But I don't know.
Hello. I know towards the end of the presentation you mentioned eclipses occurring with other stars. Are they the principal way by which we discover those stars, exoplanets?
So initially, we were able to detect the largest planets, the so-called super Jupiters. And the way we detected, this is getting technical, so anyway, so when a planet orbits a star, it forms what is called a two-body problem. And there's a center of mass of the system somewhere in the line between the two. If the planet is large enough, the star itself orbits that center of mass. So it's possible to see the wobbling motion of a star. You don't see the planet, because that star is very far away, but you see the wobbling of a star. The wobbling of the star, according to the laws of physics, can allow you to determine not only the mass of the invisible planet, but also how far it is from the star. With this visual part, the eclipsing of a star by a planet is just easier to measure. And we have very, very accurate, very sensitive measurements of the brightness of a star. So we're able to identify slight dips and how long those dips last.
Great, thank you.
Is there an expiration date on the eclipse glasses? Can we keep them for maybe the next one?
If your eclipse glass shows ISO 12312-2, then they could have been made before 2015, in which case the solar eclipse glasses may last about 3 years. If they show 12312-2 and then 2015, they were made after 2015, and the solar eclipse glasses are expected, for that kind of solar eclipse glass, is expected to last 10 years.
And also, should we be looking at the sun during the 4 minutes of the total eclipse, or should we look at the land, or, because I heard there's a shadow dance going around on the land.
You know, during the partial phase, it's about an hour. So you'll be able to look at the sun, the various stages of the partial eclipse. You can remove your eclipse glasses and look around, right? And you see shadows growing around you, and you pay attention to the birds, and so on and so forth. So yeah, there's plenty of time during the partial phase of the solar eclipse.
All right, thank you very much.
And I would be interested to see the birds that started singing, you know, the nocturnal birds at the end of the solar eclipse. Wait a minute, that was a short night.
Yeah, I heard the chickens go back into their coop during the totality. I guess they go into the coop.
So yeah, during the partial phase, I would encourage you to experience everything that you see around you.
Any other questions? Oh, back of me.
So how rare is this solar eclipse? Like total solar eclipse?
On average, somewhere around the world, there's 1 to 2 solar eclipses occurring every year. Some years there are none. Some years there are 2, some years there are 1. The location around Earth can be predicted by knowing to which Saros series it belongs. But other than that, it's a rare event. I showed you the map, the 5,000-year map, and most of it was blue. That's less than 5 solar eclipses in a period of 5,000 years. I don't know about you, but that's pretty rare. So on Monday, you are truly going to see something rare. And just experience this.
So when is the next time this area will experience a total solar eclipse?
So the next solar eclipse hitting Vermont, I believe, is in 2079. Do you remember, Liz? Yeah, but it will be an annular solar eclipse that will clip southern Vermont. So Burlington will be in the partial solar eclipse portion. The next total solar eclipse going over Burlington will be well into the next century.
When was the last time that happened?
1932 was the last total solar eclipse hitting Burlington, I believe.
Thank you.
There was a question, Liz, over there.
How prominent will something like a solar flare or gas emission be if they pop up?
So these are rare events. They're difficult to predict. They're often associated with the visible, the sunspots at the surface of the sun. I don't know if, let me check, let me do something here. Darn PC. All right. Network. That's not good. Okay. Oh, I'm back here. Let's see here. Yeah, unfortunately, right now there are only a few sunspots visible at the surface of the sun. I suspect since we're entering maximum phase, a bunch of them are on the backside of the sun. The sun rotates once every 28 days about. So those sunspots could come back and be visible in front. And it's the sunspots that are at the edges on the way toward you that if they emit a coronal mass ejection, we might be affected. And that's where the solar flares come from. There are some technical aspects associated with the sun's cycle and so on and so forth. So when there are many sunspots, the magnetic field of the sun is very turbulent. It's very active.
I think we have time for one more question, if anyone has one. Seeing none. Thank you very much, Dr. Brizard.
Well, thank you for coming. We have no idea what it looks like out